All right, so we're going to continue with our test for convergence. So this one is the integral test. And what it basically tells us is that we take the limit of an integral and it converges to a specific constant, then that means that the infinite series does converge. So let's look at an example of this. Suppose that we have an infinite series, as you can see, an, and we're assuming that there's a function f and a positive integer n, capital N, where we know that f is continuous but decreasing, and it is equal to each of the individual terms in the infinite series for all integers past that constant n, capital N that is, then only one thing can be true. Both of them are either going to converge or diverge. It can't be the case that one does and one does not. They're both going to converge or they're both going to diverge. So let's say if we have something like this, the infinite series 1 over n cubed, which starts at 1, by the way, if you notice, because if n equals 0, then this gives us division by 0. We want to know if this infinite series converges or diverges. So we're going to convert this into an integral. And if you notice, the integral is going from 1 to infinity, just like the infinite series, because remember, an integral itself is considered to be an infinite sum. Now we're going to take the limit of that expression, and the integration interval will be from 1 to b. Okay, so in other words, b is converging to infinity. And so, as you know, based on the power rule, the integral of 1 over x cubed is, as you can see, 1 over x cubed is equal to x to the minus 3. And based on the power rule, we can solve for that as x to the minus 2 over negative 2. Or you can rewrite that very simply as negative 1 over 2x squared, which you see here. And now what we're going to do is evaluate this in the range from 1 to b. Okay, let me just move these so you can see what I'm doing. So in other words, you'll have the first term will be negative 1 over 2b squared. The second term, we're subtracting a negative number, so it becomes positive. And then we'll have 1 over 2 times 1 squared. So we have negative 1 over 2b squared plus a half. And we're going to take the limit of these two. The second term is a constant, so that will just stay as a half. But the limit as b goes to infinity of negative 1 over 2b squared will just be 0, because the b is becoming infinitesimally large here. And so for that ratio has to be 0. So the final result is a half. So in other words, this proves to us that this integral in the upper left-hand corner converges, which implies that so does this infinite series. Okay. Now we have the ratio and root test. These will prove to be very, very important because they can be used in a lot of different situations. What we're doing here is we're creating a ratio. We're taking the limit of, as n goes to infinity, of 2 consecutive terms in our infinite series. And we're going to define that limit as rho. Okay, this is the Greek letter rho. In statistics, you've probably seen this used to represent the correlation between two variables, but here it's being used in the so-called ratio test, and the sign of this rho is what will tell us if our series converges or not. Also, this doesn't work unless the terms are non-zero. Okay, 0, because then you risk having division by 0. So in other words, we have to exclude 0, but other than that, this works for all other values. So here's the range of possible values within which this infinite series converges. Okay, for anything else, actually, it's more complicated than that, because there's 2 other possibilities. If rho is strictly greater than 1, or possibly equal to infinity, then the series diverges. But it turns out that if it's exactly equal to 1, then the test is inconclusive, which means you have to try something different. It basically just means that it could go either way. It doesn't tell us what we need to know. So let's try that with this case. We have n cubed over 3 to the n. We want to know if this infinite series converges or diverges. So here's what we need to do. Given that the series is n cubed over 3 to the n, we can write a general term any term an is equal to n cubed over 3 to the n, which implies that an plus 1 will be n plus 1 cubed over 3 to the n plus 1 power. So what we're going to do here is construct the ratio in absolute value, the absolute value of that ratio. First, we're going to do some simplification, of course. We're going to, instead of dividing by n cubed over 3n, we're going to multiply by the inverse, which is 3n over n cubed. So let's look at this more closely. Why don't we do this? Let's rewrite this as just to make it a little easier to see what's going on. N plus 1 cubed over n cubed times 3 to the n over 3 to the n plus 1. Now, clearly, the second term is just equal to 1/3. Actually, this first term doesn't reduce, does it? No, so you end up just with this. You've got this, which is the equivalent of saying 1/3 times n plus 1 cubed over n cubed. So the 3 got moved inside here, as you can see. So you could easily write it as n plus 1 cubed over 3n cubed. Anyway, so let's take the limit. Oh, by the way, you can still move this 1/3 outside of the limit. So let's try that. And then, see now, the problem here is that the way it's written, we're just going to wind up with infinity over infinity. So what can we do about it? Okay. Well, let's see. Here's an idea. N plus 1 cubed or yeah, so in other words, we're gonna it looks strange. We're gonna factor n out of n plus 1. You'll see why in a second. So that, in other words, the numerator is now, instead of n plus 1 cubed, it's n times 1 plus 1 over n cubed. You can see why we're doing this because, well, all right, we'll get to that in a second. In the denominator, we'll leave it as n cubed. And so this, and then we'll apply the cube to the n and the 1 plus 1 over n. So, I get what we're trying to do. You see what's happened here? These will cancel each other out. And what's even easier about this is that we know that this term, okay, this took a lot of cleverness, I must say, is just 0. So ultimately, we're going to wind up with 1/3 times the limit of 1 as it goes to infinity. So we just end up with 1/3 times 1, or just 1/3. Now, remember, we did say, now this is that row that we defined earlier. Okay, this is not the limit of the series or anything like that. This is rho, that measure that we just created here. So remember, the whole idea here is that rho just needs to be between 0 and 1, not including the 1, in order for the series to converge. And that's the case here because rho is 1/3. So remember, the rule is that the series converges. And that's all we need for now. Okay. Oh, another test. There's so many of them for convergence. What if we have another series of non-zero terms? And here's what we're going to do. Instead of having a ratio, we're going to take the nth root of the absolute value of an. And again, you notice the rule is the same. If we have a row between 0 and 1, not including the 1, then the series converges. Otherwise, oh, and this is the same too. If a row is strictly greater than 1 or row is equal to infinity, then the series diverges. If row equals 1, the test is inconclusive. So in that respect, the decision rule is exactly the same. All right, so look at this thing. Now you can see why we're tempted to use the root test, because we have very high exponents for in the numerator and the denominator. And so here's what we're going to do. We're going to create a row measure by taking the nth root of this expression. Okay. Now, of course, don't forget it is the absolute value, because otherwise we could end up with a negative number under the square root. We don't want that. So the ends essentially cancel each other out. You know, it would be like having the cube root of, oh, I don't know, 8 over 27. Which means just 2/3. Okay. So you end up just with the limit. Now, of course, you can see here, if this is our limit, we've got direct substitution will lead us to infinity over infinity. So what we're going to do is we're going to divide the numerator and the denominator by the highest exponent, which is n squared. So we end up with the limit of 1 plus 3 over n divided by 4 plus 5 over n. And the beauty of this is that the limits here, as n goes to infinity, will both be 0. So we ultimately end up with 1/4, which falls within the range that we're looking for. And therefore, this series converges. And that's it. So that one is done. Okay, so now we're in pretty good shape with our tests for convergence for infinite series. Now, of course, which test do you use? It depends on what situation you're facing. Obviously, you want to pick whichever one is the most convenient for the particular circumstances you're dealing with. Or you can try multiple ones to confirm each other. But that's our end of our discussion of chapter 5. So we're going to introduce 6 now. And in 6, we're going to introduce something called power series, which are a special case of our infinite series that we've been covering in chapter, the second half of chapter 5. In particular, we're going to introduce 2 incredibly useful series called the Taylor series and the Maclaurin series. Why are they so useful? Well, among other things, we can use them to create approximations to very complex functions. And so, you know, there's a lot of applications where these can be very, very helpful. But these power series, although they're still infinite series, they have a particular property that makes them power series. And so what we want to do is explain what a power series is. It is basically it's an infinite polynomial when you look at it. It's written in the following way. We have some constant Cn, starts at 0, goes to infinity, and then we have x raised to the nth power. So it is indeed an infinite polynomial. That is what we mean by a power series. Okay, it's an infinite series, but it's a special type of infinite series. And of course, as you can imagine, there's many different kinds of infinite series. Some are more useful than others. This one will prove to be incredibly useful for a lot of applications. So here would be a good example. And let's say we had something like this. Let's say that this C is just 1 across the board. Okay, it's a constant, it's just 1, so we end up with something relatively simple. This infinite series of n equals 0 to infinity of x to the n, which is just 1 plus x squared plus dot 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 all the way up to infinity. So here we can prove that if the absolute value of x is strictly less than 1, then the series converges. If the absolute value is greater than 1, then it diverges. Okay. Now, when we have a form like this, there's a way we can write this in a more general form. We say that x is centered at x equals 0. You'll see what that means in a minute. Okay, centered at 0. In order to explain that, we have to see what it means to be centered somewhere else. So if the series is centered at A, for example, that means each of these x's is being replaced with x minus A, as you can see. So let's put them side by side so you can compare them. Okay, so in other words, the one on the top is centered at 0. And the one down here is centered at x equals A. So in other words, the centered at 0 case is a special case of centered at A, because we could have A equals 0 if we want to. All right, so those are the two types we might encounter. And here's a fun example. Suppose we have this power series. We have 1 x to the n over n factorial, which equals 1 plus x squared over 2 factorial plus x cubed over 3 factorial, et cetera, all the way to infinity. And so here the power series is centered at x equals 0, because if not, you would have had something like this. Okay, that's what it would have looked like had it been centered at A. You're just replacing all the x's within, the x's become x minus a's. So we'll see that on the next slide. We have this one. Now, this one is not centered at 0 because we have the x minus 2 here. Each x minus 2 is raised to a different exponent. So here we say that this power series is centered at x equals 2. All right. So far, so good. Now, convergence. Now, of course, this is a series. We want to know if it converges. That's awfully, awfully important. So a power series may converge for some values of x and diverge for other values of x. If the power series is centered at x equals a, when x equals a, all terms except for c0 are equal to 0, which means what that ends up telling us is that the series converges to c0 when x equals a. Okay, you can see why. I mean, if you look at this thing, like for this one, if you let x equal a, all these terms will drop out except for the c0. Okay, so when it's centered at a, if x is equal to a, that means they'll all drop out and you'll converge to just the constant c0. So, and this will be true no matter what value of a we've chosen. So this shows that a power center, at the very least, always converges at its so-called center. Okay, a is defined as its center. By the way, we're going to see a lot of examples later on with specific cases, and it'll be easier to see what this is all about when you have graphs in front of you. Right. When you have graphs, it's so much easier to see when we have specific examples. You'll get what's going on here much more quickly. Now, of course, even though they can converge at the center, or they do converge at the center, many of them can converge for more than one value of x. So if that's true, then it converges for all real numbers, or else all of them within a specific interval. Okay. It's not like it's got one or two. It's either, it's still going to be an infinite number. If it's all the real numbers within a finite interval, we're still looking at an infinite number of values of x. So what that means is if the power series converges for at least one value other than its center, it will have an infinite number of values of x at which it converges. Now, as far as this power series, this is the one that's centered at A. Which is the most generic case or general case. It's guaranteed to have one of the following properties. Either it converges at x equal a and nowhere else. It converges for all real numbers. Or there's a range within which it converges and it diverges outside that range. So you've got the three cases, either only at the center, everywhere, or just within a given interval. Now, the interval is defined in terms of R. That capital R determines the range of possibilities within which it converges, and then everywhere else it diverges. Okay. So now, when the series converges for a real set of numbers, that is known as the interval of convergence. Okay, so like here, let's just say this is what we're looking for. Oh, let's just say that the R is 1. That means all the A's within 1 of X, and those less than 1 away from X, are going to be the interval of convergence. So it means it would be, let's see, here's our A. If you have, you can rewrite this in two different ways. Right. Okay. So that's your interval of convergence. Okay. So here's a graph that might help illustrate this a little bit better. We've got the first case where it converges only at A, and the second case it converges everywhere. In the third case, it's only within that range. So those are the three possibilities. Okay. So the third case is this one, where there's a specified range of values within which it converges, but everywhere else it diverges. So those are the three possibilities. Only A, everywhere, and only in that interval. Now, sometimes all we need to know is what is the interval within which it converges. It turns out that our old friend, the ratio test, can be used to help us here. So here's that ratio test again. Rho is defined as the limit as n goes to infinity of a over an plus 1 over an. And of course, this is the rule. This guarantees that an converges. Remember, though, it diverges if rho is greater than 1. And finally, and of course, remember, rho equals 1. The test is inconclusive, which means we have to try something else. All right, it's always easier to do these with an example. So let's use this series. And we'll construct a ratio. Okay, that's any two consecutive terms. So we have in the numerator, the denominator is the original series x to the n over n factorial. In the numerator, we have x to the n plus 1 over n plus 1 factorial. Now, we can rewrite this. In fact, let's do this. The denominator is here, so we can rewrite it like this. And then we can further simplify it. By writing them like this. So this one is pretty straightforward. This is just x. What about this one? N factorial over n plus 1 factorial. Well, n factorial, as you know, is just n times n minus 1, n minus 2, all the way down to 1. N plus 1 factorial is 1 plus 1, and n minus 1, n minus 2. So all these terms will cancel out. And you'll end up with 1 over n plus 1. So this ratio that we constructed here is the same thing as x over n plus 1. And of course, if the limit is being taken with n going to infinity, that means this limit is simply 0. And that counts for our test. And so it converges. In fact, it converges for all real numbers. And therefore, the interval of convergence is said to be the real numbers, or simply r equals infinity. Now, here's an interesting case. This, for the first time, we're going to see one of the most important uses of power series. We're going to take an actual existing function and rewrite it as a power series. Okay, so like here, for example, the infinite sum, infinite series, x to the n power, is the same thing as 1 plus x squared plus dot, dot, dot. But we'd like to reduce that to something more manageable because this on the left, we have an infinite number of terms. So you might recall that a geometric series that looks like this converges if the absolute value of r is less than 1. And if that's the case, this is what it converges to. This is a specific constant, a over 1 minus r. So here, I think you'll agree, based on the definition of geometric series, this up here, that if a equals 1 and r equals x, then this is a geometric series. And therefore, as long as the absolute value of x is strictly less than 1, this expression converges to this. So in other words, the entire sum, no matter how many terms there are, there's an infinite number of terms. So let's just say that it was 1 plus a half, plus a quarter, plus an eighth. Whoops. This means that you have a geometric series where a is 1 and r is a half. And since r is less than 1, this converges to a over 1 minus r, which is 1 over 1 minus a half, which is 2. Okay, now there's that infinite sum will end up converging to 2. Interesting. How do we know? I mean, so the beauty of this is that we don't have to take any limits, although we already had to know that this infinite geometric series converges to 1 over 1 minus x. So that was something that had to be demonstrated. But once you know that, you can take the series that you have and recognize that it is a geometric series. And all of a sudden, before you know it, you have the ability to figure out what these numbers or their sum adds up to in the limit. And so this function then is equivalent to this geometric series. Now, the reason why that might matter is because I can actually use the first few terms here to come up with a very reasonable approximation to this function, if there's some reason why I need to do that. Okay, in other words, as you get further along, the terms are getting smaller, obviously. So if I only need a certain amount of accuracy, then I could actually replace this 1 over 1 minus x with the first few terms in this series. Interesting. By the way, here's the graph. This is what I was alluding to earlier. If you notice, what they're doing here is saying, listen, this is the series that we're looking at. 1 plus 1 over x plus 1 over x squared plus 1 over x cubed. And so what they're saying is, we know oh, wait, what did I do? No, sorry, these are, it's not 1 over. But the x's are themselves fractions. That's all right, sorry. 1 plus x squared plus x cubed, where x, okay, so these are fractions. So what that means is that as I keep raising the exponent, these numbers will keep getting smaller. So these are partial sums. So S2 would be 1 plus x. S4 would be 1 plus x squared plus x cubed plus x to the fourth. And so what they're showing you is that this is the actual function. These are the partial sums. So here's S2. It doesn't really look, it's a straight line. Of course, it doesn't look like the original function. But here's S4. It's starting to look a little bit better. And S6, it's even better. So what you're seeing here is that if we keep increasing the number of terms in our partial sums, we're going to get progressively closer to the actual function. So depending on how much accuracy you need, you can use any one of these partial sums or one of these partial sums to approximate the function that you really need. And also, if you notice, within a wide range of values here, even S2 is pretty close to that function, isn't it? But after you move a certain distance outside here, you notice the approximation starts to break down. But within this range, even S2 does a really good job of approximating f of x. So now how about this one? What if we wanted to turn this into a power series? Well, we might be able to turn it into a geometric series if we think about it. We like geometric series. They're easy to work with. And they're not that hard to find in the real world. What would we need, though, to make this into a geometric series? Oh, well, how about this? Instead of thinking of it as 1 over 1 plus x cubed, let's think of it as 1 over 1 minus x cubed. Now, remember, if r is the absolute value of r is less than 1, this expression is the series converges to this expression. So this could be our a, and this could be our r. Not, yes. So then if that's the case, let's make those substitutions into the first few terms of this geometric series. And let's see what do we end up with. So the a's are the 1s, the r's are now negative x cubes. And assuming that this negative x cubed is the absolute value is strictly less than 1, we know that this series will converge to 1 over, or a over 1 minus r, which is 1 over 1 plus x cubed. So basically, what we've done think of this as this is r squared, this is r cubed. If a is 1, this is what we have. So it is a geometric series where the r is negative x cubed to the end. So that means that these are equal to each other. Interesting. So again, if there's some reason for it, you could approximate this function with partial sums based on this infinite series. You could use S2 or 4, it doesn't matter, S10, whatever you need. I don't think we have a graph for this to show it, but as you saw before, at least within certain ranges of values, that means this geometric series, even just the first few terms, should give us a very good approximation to this function. Well, all right then. Now, power series have their own set of properties. We have, let's say we have these two power series. And remember, we need a constant. We need an x to the n power to have a power series. If they converge to functions f and g respectively over the same interval, that's only if they both converge, then the series consisting of their sums or differences will converge to the sum or the difference of f and g over that same interval. Okay, so, I think that's pretty sensible. This one converges to f. This one converges to g. So it stands to reason that a series consisting of their sums so the terms would be like, for example, the first one would be C0x. The first term would be C0 plus D0. Then you'd have C1x1 plus C D1 X. Actually, this probably should be written as C1 plus D1 X. Then you'd have C2 plus D2 X squared, et cetera, et cetera. Well, then this sum converges to the sum of the two individual series, the functions that the two series converge to. Now, what else do we need to know? If we have bx to the m power multiplied by cn to the x to the n, then this converges to bx to the m f of x. Okay, because we're assuming that this piece by itself converges to f of x. So it stands to reason that you would simply multiply by this term. And for here, it's the same idea. If converges to f of bx to the m, as long as this is in the interval I, okay. So it's the same idea, except that the bx to the m is being raised to the nth power. Now, these can be multiplied together as well as added. Okay, so if that happens, this is what you'd end up with. All right, so the terms would be C0, D0. The next term would be C1, X. Oops. um, no, actually, you know what? No, this is not working. What we should do is this. Remember, these are the products of sums. So in other words, I'm not doing this correctly. It should be C0 plus C1x plus C2x squared plus dot dot dot. All of it multiplied by D0 plus D1x plus D2x squared plus. So in other words, you're going to get a lot of cross product terms in here. This is why it looks a lot more complicated, because if you multiply these, you're going to end up with these two terms for x, and then you'll get 3 for x2, and it'll continue to expand. But you can only do this if they converge within the same interval. Okay. Now, believe it or not, you can actually integrate and differentiate a power series. It's not just restricted to functions. Differentiation and integration can be applied here as well. In fact, we're going to need to do that, as you'll see later on, to get some of our most important results, in particular for the Taylor series and the Maclaurin series. Okay. So, all right, let's see. So how exactly would that work? Now, of course, we have to make an assumption that this in the power series converges on an interval a plus and minus r. And so what you have to do is apply differentiation on a term-by-term basis and then add them up. But it's exactly what you'd expect. You're basically just applying the power rules, because remember, this is nothing but an infinite polynomial. So like here, for example, you can see the derivative of C0 is just 0. And then here, now this is with respect to x, by the way. This is f prime of x. And you can write this in the most general possible terms as using the power rule n Cn x minus a to the n minus 1 power. All right, and then you can follow the terms will follow from that. But what you're basically doing is taking the derivative of each one using the power rule. And if that's the case, then of course you could do the same thing with integration. How would that work? Well, you're applying the power rule for integration instead of differentiation. Okay, so yeah, this is what you'd end up with. All right, so all right, I'll tell you what, why don't we knock it off right here? We have some very important examples coming up, plus we want to introduce the Cloran and Taylor series. That's really the highlight of this part of the chapter, but I think we have enough to think about for now. So we'll stop here, and then we'll do some more examples of how to integrate and differentiate a power series before we move on, because we're going to need to do this for the rest of the chapter. So we'll stop here, and then the next time I see you, we'll finish this part up, and then we'll introduce Taylor and Maclaurin series, because they're the ones that we'll use most frequently to develop representations of functions using these power series. All right, so I'll see you all next time.